Welcome, everyone. This is another Global Poisson. And this week we have Mikhail Semenov-Tian-Chanski, who's going to talk about quantum total lattice, a challenge for representation theory. Okay, go ahead.
So thank you very much for your invitation. And well, it's not quite the topic of this Poisson seminar, but of course, quantum total lattice is something which is rather near to the Poisson geometry, and in many ways, total lattice can be regarded as one of the most famous and most important examples of a quantization of a well-known classical system. And this was, in fact, the discovery made in Kasdan and Kostant, and then by Kostant, mainly by Kostant. First of all, they have found an interpretation of quantum total lattice in terms of coadjoint orbits of the Barrel subgroup of a semisimple Lie group, and then also in terms of Hamiltonian reduction. And this Hamiltonian reduction, it survives quantization, and this was the very, very important remark made by Kostant that quantum total lattice remains completely integral in the quantum case. And he also noticed its intimate relation to the theory of Whittaker functions and semisimple Lie groups, which by that time was already quite well established. And then when we have heard of this most interesting development in Faddeev laboratory in Leningrad, this was an indication that classical integrable systems, which are integrable by means of classical inverse scattering transform, also survive, can have got their quantum counterparts, which are again integrable. And it was the starting point of the development of the so-called quantum inverse scattering method. And on the other hand, the theory, the quantum theory, the theory of quantum lattice, to the as described by Kostant, it belongs to the area of well-established representation theory of semisimple Lie groups, and this allows to develop a spectral theory for this total lattice. I mean, open total lattice. There is a much more complicated and very interesting system, which is called periodic total lattice, and which is related to infinite dimensional Lie groups and Lie algebras, the loop algebras. And now the open total lattice is a special example which is related to finite dimensional semisimple Lie groups, and in that respect it's much more simple than the periodic total lattice. And now, by that time already, the theory of the representation theory of semisimple Lie groups has been developed for many years, by starting with the works of Bergman, then Gelfand and Pyatetsky, then especially Harish-Chandra, and this was and then finally one of the most important discoveries which was made in the this scattering theory, in this representation theory, was the factorization formula discovered by Gindikin-Karpelevich around 1962. It was a dramatic story. Harish-Chandra has developed his theory of spherical functions, which depended on the properties of a certain special meromorphic functions, which was implicitly given by by a multidimensional integral. And in his original work in 1958, Harish-Chandra wasn't able to prove all the necessary properties of this Harish-Chandra C function, which are needed to complete the proof of the spectral theorem. And then, rather surprisingly, it appeared that this C function can be explicitly computed in terms of gamma functions. So it's a product of functions of one variable. And this results in a very important paradigm in the representation theory, which means that asymptotically, the scattering properties of associated with the wave packets, which describe eigenfunctions of continuous spectrum in this representation theory. These wave packets are very much complicated, but they have got some important properties, and in particular, their asymptotics is much more simple, and it's described by factorized scattering, as physicists say, and which means in particular that the scattering matrices in this case are products of functions of one variable. Now, just a short overview of this representation theory. We start with a semisimple Lie group. There is the center of its universal of the universal algebra U of G, and there is a maximum compact subgroup of G, and then the spectrum analysis of the center of universal algebra is more or less equivalent to the decomposition of L2 of on G into irreducible components. Well, in general, these Laplace operators are not elliptic, and just to circumvent this difficulty, one usually considers k-finite eigenfunctions. So we combine the spectral decomposition of the center with the decomposition into k irreducible components. And then basically we deal not with arbitrary functions on the Lie group, but with vector functions on G over K on the symmetric space, which is already a Riemannian space, so the ellipticity problem is circumvented. Simply we need not scalar functions, but eventually some sections of some bundles over the Riemannian symmetric space. And the structure of the joint spectrum of the center in this L2 is rather complicated. There is a discrete spectrum. Sometimes it's non-empty if and only if there is a compact Cartan subgroup. And then there are several branches of continuous spectrum which are associated with the so-called cuspidal parabolic subgroups of G. And each parabolic subgroup is cuspidal if it's well, we just take this Langlands decomposition. There is this subgroup L, which is reductive, and if the discrete spectrum of this center of corresponding enveloping algebra of M is non-empty, then it's or otherwise, if M contains a compact subgroup, then this is called a cuspidal subgroup. And for various cuspidal subgroups, we just can induce representations from the representation of the discrete spectrum of M, which are extended to P in a natural way. This brings into play, of course, the extra spectral variable, which is called lambda, which is the character of the split Cartan subgroup in this decomposition. And then eventually we get formal eigenfunctions, which are given by this more or less explicit formula. Harish-Chandra calls this eigenfunctions the Eisenstein integral by analogy with Eisenstein series, which one encounters in arithmetics. Of course, this is a complicated integral, and it's rather hopeless just to try to compute it explicitly. Now, to further simplify the problem, we just can consider the simplest case. This is the case of class 1 representations which correspond to the minimal parabolic. And in that case, the subgroup M is in K, and the dimension of the continuous spectrum is maximum, and it's equal to the split rank of the group G. And then we can just take a trivial representation of both M and K, and in this way we get a particular case of this Eisenstein integral are the famous spherical functions of are now semisimple groups, which are in fact be invariant with respect to both left and right translations by the compact subgroup K, and it's an eigenfunction of the ring of differential operators on Z of G, or equivalently of its quotient, which is the ring of invariant differential operators on the symmetric space. And this function is in fact a matrix coefficient of the principal series representation, just one associated with this minimal parabolic. Is a standard representation of continuous series of the group, and by common wisdom, all matrix coefficients of such these representations are in fact eigenfunctions of this algebra of invariant differential operators. This is a kind of, it follows from the Schur lemma, in fact. And so in this way, we get, if we just act by a differential operator from invariant differential operator on this function, we get some eigenvalue, and this, in fact, provides an isomorphism of our algebra of differential operators onto the algebra of symmetric polynomials on the split Cartan, on the dual of the split Cartan subalgebra. And this is the famous Harish-Chandra isomorphism. In fact, one can prove, and it's a very non-trivial theorem, that this is not this assignment can be inverted, and it's an isomorphism, and its image lies in the subalgebra of polynomials on A star, which are invariant with respect to the action of the variable. And there is another interesting matrix coefficient. This is called the Whittaker function. Now we just take, say, we take this Langlands decomposition of the minimal parabolic. We take the opposite important subgroup, and we take a character of this subgroup. And in this way, we can define a Whittaker vector. Now, after an equivalence, in this case, there exists only one character of a important subgroup, which is non-degenerate, which is called the principal character. And then we just can define the Whittaker vectors as it's vector, which is the eigenvector of this important subgroup in the representation space, say, of continuous series. And then if we take the matrix coefficient of this form, we get a formal integral representation for this Whittaker function. It's a rather subtle question because the Whittaker vector doesn't lie in L2, unlike the spherical vector, which is a square integrable function. But for Whittaker function, one has to take more care. Sorry?
Sorry. Just one question. I think the
Yes.
sound is not great. Your mic. Could you check whether your I don't know whether your mic is there is no extra sound, because when you were speaking there was some kind of vibration. But yeah, if possible, would be better to eliminate it. But
it's raining outside. Maybe you just see the raindrops, which are quite near the microphone.
Okay. So that's you're saying that the physical world is kind of intervening with our virtual world. Okay.
Yes.
Okay.
I just return to this formal integral representation. There is a special theory which is well developed, which amounts to just the study of convergence and analytical continuation of this Whittaker function. So this may be done, and then our Whittaker function satisfies this functional equation. It's k invariant on the left, and it's covariant with respect to the action of this new potential group on the right. And now it's just what physicists call it's an eigenfunction of continuous spectrum of our invariant differential apparatus. So it shouldn't lie in L2, of course, and it doesn't. But following the general wisdom of spectral theory for apparatus with continuous spectrum, we must form wave packets, just must average these functions over lambda with some sufficiently good amplitude A of lambda. And then the goal is to prove that these wave packets, they behave already quite well. They lie in O2, and again, as Harish-Chandra knew perfectly well, because he was at some early point of his career, he was a PhD student of Dirac, so he knew quantum mechanics very well. And the point is that to study the spectral theory associated with the continuous spectrum, one has to look at the asymptotics of these wave packets or of these eigenfunctions of continuous spectrum when the argument goes to infinity. They're completely determined by the restriction to this split Cartesian group, and the split Cartesian group is the exponential of the split Cartesian algebra, and inside this split Cartesian algebra there are Weyl chambers, and now we just take the positive Weyl chambers, and we look at the asymptotics inside this, when the argument A lying inside this positive Weyl chamber is large. And same thing applies to spherical functions. And we can just take the radial part of the Laplace-Beltrami operator on our symmetric space, and there is an explicit formula for G equal to GLN. Here is this formula, and if we just make a standard change of variables, just multiplication by some factor, which I denote by J, then we get this very famous Hamiltonian, which is called the Sutherland Hamiltonian, which is a special case of a more general class, which are called Kalodger-Moser Hamiltonians. And this is a well-known fact that the theory of spherical functions is more or less equivalent to the spectral theory of this Sutherland system with repulsive potentials, which are just these hyperbolic signs squared. And for this case as well, we must look at the asymptotics, the eigenfunctions, the spherical functions themselves. They are not in L2, but we must take wave packets and look at their asymptotics. And for the case of Whittaker functions, again, we can restrict our Whittaker functions to A, to the Split-Cartan subgroup. Then we pass to the exponential parameterization, and then we end up with this famous Hamiltonian, which is nothing but the Hamiltonian of the open Toda lattice. It's just the kinetic energy, the standard term, plus the potential, which describes interaction of the nearest neighbors on the Gindikin diagram of Gelfand. And if we just add one more root, so all these functions of x are just simple roots of our algebra, and if we just add one more root, which is alpha naught, then we get the affine root system, and this represents a major change in our picture, because already the affine root system is the root system of the affine Lie algebra, Gelfand tilde, and this is another story which I shall not almost speak about today. And so, as I have already said, we must consider wave packets of this form and look at their asymptotic behavior when the argument G, which is, now we just restrict our argument to the Split-Cartan subgroup, and it goes to infinity. And the key role in this study of the asymptotics plays the Weil group, which has, on the one hand, it's just the geometric symmetry group of the root system, and also it's the Galois group of the extension associated, as you remember, with the Harish-Chandra isomorphism. And in particular, along with each point lambda in the dual space of A of the Split-Cartan subalgebra, you get all its images under the action of the Weil group, and all representations associated with these images are in fact equivalent. And this equivalent is explicitly realized by intertwining operators, which were introduced by Gelfand under the name of horospheric automorphism operators. And it's a special story which I cannot discuss now. In some sense, these intertwining operators, they are scattering operators for some well-posed scattering problem. And there are some explicit formula, which require all these formulas. They are written here formula. They require much work when one wants to understand their convergence, etc. And the analytic continuation of these intertwining operators is a matter of great work, which was mainly done in the late 60s and early 70s. And if we compute the action of this intertwining operator on the spherical vector, we get well, the spherical vector associated with the reflected point s-1 applied to lambda times some interesting function, which is explicitly given by this integral. Again, this integral is convergent in the complex domain where lambda, imaginary part of lambda lies in some appropriate Weyl chamber, and then we have to analytically continue these functions. It's again, it's a matter of work which was partly done by Harish-Chandra in his famous papers, and in particular, if S is the longest element, then we get this famous Harish-Chandra function, which is given by the integral of this maximal nilpotent subgroup. Very explicit formula, but rather it's not quite transparent in this form. Same thing happens for Whittaker vectors, which introduces some other scalar factors which are obtained by the action of these intertwining operators. So in this realization, we have just simple symmetry with respect to the action of the Weyl group for spherical functions, and some fancy meromorphic factor for Whittaker functions. And now there was a just tour de force which was made by Gindikin-Karpelevich following some earlier discoveries. It happened that Harish-Chandra himself has computed this C function in the rank 1 case, and there it becomes just when the radial part of our Laplace operator is in fact an ordinary differential operator, and so we are in the realm of spectral theory of ordinary differential operators of second order, and then Harish-Chandra computed these functions which coincide with the Yost functions for this operator. And he wasn't able to do it in the general case, and then this is the famous Gindikin-Karpelevich formula, which expresses explicitly our function in terms of some product of functions of one variable. There is very specific functions which are gamma functions or beta functions, Euler beta function, in fact. And same thing, well, just it happens that the intertwining operators, which are given by this formula, they again can be reduced if we take a reduced decomposition of this Weyl group element S into simple reflections. Then, accordingly, the intertwining operator is decomposed into a product with some classical twisting of intertwining operator in the rank 1 case, and these are so everything is reduced to the rank 1 case, and then in the rank 1 case, lambda is just a scalar variable. It's just replaced by this this combination, the scalar product of lambda with some root, and this was a great discovery. So we know that eigenfunctions are very complicated, but they're asymptotics, and these C functions, they in fact appear in the asymptotics of the spherical functions and also the Whittaker functions. This asymptotics is much more simple, and in the asymptotics we have factorized functions which are products of functions of one variable. Just one fancy remark. I have written this Whittaker function equation for the Whittaker function is rather non-trivial, with some factor which can be computed, but which is non-elementary. But as it happens, there is another possible, and this realization of the Whittaker function itself is an entire function of lambda. But there exists a different normalization of the Whittaker functions. We can sacrifice the analyticity, so it's already meromorphic, but instead it satisfies a very simple functional equation, the same as for the spherical function. And of course, this new function psi should be proportional to W because there is just the multiplicity is 1. So there is just one up to proportionality, there is just one Whittaker function. And in fact, it's enough to just multiply our function by the denominator of the Harish-Chandra function C, and this is the formula, and it makes it satisfy this very simple functional equation. And so this was the state of affairs following the works of Harish-Chandra and of Gindikin-Karpelevich. This was kind of paradigm, which means that we deal with eigenfunctions, which may be complicated, but which have simple asymptotics, and the asymptotics we encounter factorized formula. And now this part of the story is perfectly well known by the experts in representation theory, but as far as I have noticed, the experts in representation theory are not aware of the sequel of the story, and this is why I just decided to write a kind of review article at the intention of the experts in representation theory, and this follows from the application of quantum inverse scattering method to quantum Toda Lattice. It's mainly took several decades. There were papers by Gutzwiller, then Sklyanin, then Pasquier-Gaudin, and finally Dmitry Lebedev, Sergei Kharchov, and others. And this was a great progress. And now this progress, as I want to, this is my point, that the implications of all these developments in the representation theory, they have still to be recognized. And of course, we know not sufficiently much to speak of the problems of representation theory and its high generality, but already this simple branch of continuous spectrum, which is dealt with in the theory of spherical functions or of Whittaker functions, is quite fascinating. And so there are the new development consists in the following 3 points. There exists the standard Toda Lattice. It's a kind of elementary quantum mechanical system which is treated in the coordinate representation. The momentum is just the derivation operator, and the potential is just the multiplication operator. And now there exists a representation in the sense of a different representation of quantum commutation relations in the sense of Dirac. And in this new representation, the algebras of quantum integrals of motion for the Toda Lattice, they are not differential operators, but they are freely generated by first-order difference operators. And in this representation, the common eigenvectors of all these of this ring of commuting difference operators, they're decomposable. They are products of functions of one variable. And again, these functions are just special combinations produced by from the gamma function. And now, again, in the logic of Dirac, one must look at the transformation operator, so which relates this new representation, the representation of separation of variables, which were first introduced by Sklanin, and this new representation is unitary equivalent to the standard, to the coordinate one, and we must compute transformation operators which realize this equivalence, and this can be done recursively. And finally, this transformation operators, they amount to a sequence of ordinary Fourier transforms. So finally, we get a totally elementary formula as a kind of Fourier transform, the classical Fourier transform of some aggregate computed, which consists of gamma functions. And this is a very unusual thing. So not only the asymptotics of eigenfunctions is factorized, but there exists this new representation of the computational relations in quantum mechanics, where the eigenfunctions themselves are decomposable and they're product of functions of one variable. This is quite unusual. And so just to give you some technical outline of how does it happen. I have not enough time probably just to finish my story. I have only 20 minutes left, a little bit more. So just maybe some of in the audience, they have heard, or of course they have heard of this quantum investigator setting. So we have start with the classical commutation relations, just the position and momentum operators, and they are arranged in this 2x2 matrix with operator entries. So the Hilbert space H associates with the commutation relation, just the quantum space, and there is an auxiliary space which is just C2, and the commutation relations between various operators here, it's encoded by some linear transformations acting in an auxiliary space. So we just take this very famous R matrix, a linear operator acting in C2 times C2, just a parameter U and formal parameter, and permutation operator acting in C2 cross C2. And then we have this very famous commutation relations. We can just interchange the order of two quantum lax matrices, and this amounts to a conjugation by this quantum R matrix. And everything is put on the lattice. So when we are at the same point of the lattice, we have this equation, and when the sites are different, our lax matrices commute with each other. And then it's a kind of property which is encoded into this procedure. Just we take this form of monogamy matrix, and then this monogamy matrix is exactly the same commutation relations as do the local lax matrices. Just this equation 23 is reproduced in this formula 24. Now we just look at this monogamy matrix. It's just a 2x2 matrix with operator entries, and its trace gives us a family of commuting operators, and we can just expand it. It's a polynomial. If we just take a finite lattice, of course, just a periodic lattice, the n is just the number of sides, then it's a polynomial, and all coefficients of this polynomial commute with each other, and in particular the first coefficient is just the the trace, and it's just the total momentum. And the second coefficient is up to this extra term. It is just the Hamiltonian of the open Toda Lattice. Not the open Toda Lattice, the periodic Toda Lattice. Well, this is the open Toda Lattice, and there is an extra term, which makes it periodic. And now we can just do the same thing for the particular matrix coefficients of our monoidal matrix A and D. So we have two families of if we just look at the commutation relations for the individual coefficients of our monoidal matrix, then we just get these formulas. So A, B, C, and D separately, they give commuting pencils of operators. And in particular, A give about just if we just want to get the open Toda Lattice, we must look at this coefficient X, and X2 is just the up to this trivial term. X2 is just the and up to sign is just the Hamiltonian of the open Toda Lattice. And the coefficients Y, they add up to X to yield the quantum integral solution of the periodic Toda Lattice. So it's a kind of just the A and D, they just match together to produce integrals of motion for the periodic lattice. But we are mainly interested in the open Toda Lattice. Moreover, they have this recursion property. The AN is equal to this combination of AN minus 1 times plus CN minus 1, and CN is up to some factor which depends on the last coordinate, the same thing as AN to the minus 1. So there is a fancy interchange of interpretations between A and C. Now we look at C, and this was a bright idea originally introduced by Sklenin. It's a polynomial in U, and it can be written in factorized form, where lambda hat are some mutually commuting self-adjoint operators, the operator value root of C. Now, these are called quantum separation variables, and spectral representation for this operator is called separation representation. This is the main protagonist of this quantum story. The new representation, which is the spectral representation not for A. The spectral representation for A gives you the eigenvalues of the eigenfunctions of Toda Lattice. And here we look for another quantum representation which diagonalizes C. And this is just the very important step. Now, just this is some sort of little operator calculus which is needed, and it's again largely due to Sklenin. We just take some special values of A evaluated at these operator valued roots of C, same thing for D, and in this way we get just two sets of operator lambda minus and lambda plus. And we can restore our operator A and D from its roots and from its special values. This is a kind of Lagrange interpolation formula. This is again due to Sklenin in its early 90s. And then we get the following algebra. These operators commute with each other. They commute with each other. These are separation variables. So do the lambdas, the capital lambdas, and the exchange relations between capital lambda and little lambda, they are given by this formula. So lambda capital acts as shift operator on the separation variables. And this is the key point. So we can pass to the spectral representation in which lambda are, the operators lambda are diagonal. So they are eigenfunctions, they are this, and so P is the momentum, the total momentum operator, and K is its eigenvalue. So it's just sort of tautology. And so we have this interesting representation of our commutation relations by difference operators. And this is something rather unusual. Now, just let me skip this, the discussion of the Plancherel mirror. I maybe return to it a little bit later. But now we can look at the eigenfunctions, and the eigenfunctions of our quantum operators. So the coefficients of A, they give the quantum mechanisms of motions for the open Toda lattice, and the eigenfunctions evaluated in these spectral representations. Well, there is a simple factor associated with the total momentum, and there are some eigenvalues which are denoted by alpha. So alpha is just the parameter. Alpha is a there's just several alphas which are together describe the spectrum of these quantum Hamiltonians of the Toda lattice. And now we just get this very simple difference equation. Well, just lambda minus is a difference operator. It's acting on these eigenfunctions by multiplying it by by the product of these elementary factors. And if we just substitute the value of this lambda minus, then finally we get the explicit solution, which gives you the eigenfunctions of the quantum Toda lattice in this spectral representation for quantum separated variables. And this is the formula. And explicitly, it's just a product of several gamma functions. And this is something which is totally new as compared to the Gindikin-Karpelevich formula. Now, not the asymptotics of the eigenfunction in coordinate representation, but the eigenfunctions itself in some auxiliary representation is given by this absolutely fanciful formula. If we look at the periodic Toda lattice, which is associated with the trace A plus D of the monotony matrix, then we again, our separation of variables is still valid. But instead of first order difference operator, we just get here lambda plus and lambda minus. These are two difference operators acting in opposite directions. So the left-hand side here is a second order difference operator, which makes much difference because the theory of this first order difference operator is elementary and the solution is immediate. It's just a product of gamma functions. It's just you can solve it explicitly. And if we pass to this periodic case, everything sounds much worse because we cannot solve explicitly this second order difference equation. And this represents a big difference and a great challenge in the theory of integral systems. You may recall that in the classical case, the Lax pair for the periodic lattice is associated with loop algebras, and its solutions requires algebraic geometry and many things, just Riemann theta functions, etc., etc. And in the degenerate case, the solution of the equations of motions is simply reduced to matrix factorization. And in the quantum case, there is a similar situation. This degeneration consists in the replacement of the second-order differential system by a first-order difference system. And so it's this much more simple and, in some sense, degenerate case, which contains all representation theory of finite dimensional semi-simple Lie groups. And what happens in the case of second-order difference operator? Well, it's a largely open question. Not much is known about it. And now, well, it's a great discovery, of course. And now we just want to ask, how can we pass from this fancy representation of separated variables into just back to the coordinate representation. And we can just we apply logic just of Dirac. We just look for transformation operators which relate different equivalent representations of quantum commutation relations. And so we just take different coordinate systems in our quantum space, which are labeled by just indicating what the complete set of diagonal observables which act by multiplication. So we have this coordinate representation in which the diagonal operators are the standard coordinates. We have separation representation, which where the operators lambda act by multiplication, and their eigenvalues are just lambda without hats. And there is a spectral representation which diagonalizes the roots of our coefficient A, and these are just the spectral representation for the open Toda, and together with its high integrals of motion which commute with the standard Hamiltonian. And now if we just get back to the formula which I have written several slides before, it's this one. This formula is just the basis of recursion. It means that to diagonalize Cn, we must solve, we must add an extra variable, and we must solve the Toda lattice with n-1 nodes, or n-1 particles. And this is the basis of recursion. So the transformations operators, they are nothing but the complete systems, just the kernel of this transformation operator is nothing but the complete system of eigenfunctions for the rank n-1 Toda lattice. Plus, there is an extra coordinate variable which is decoupled. And so we just write this transformation operators using the Dirac notation, and we apply the chain rule, and so this is our eigenfunction parameterized by alpha in the coordinate representation is given by this formula, where I have not said anything about the measure. The measure is the famous Poincare measure, which has been computed by Harish-Chandra in his time for spherical functions, which is the same for the Whittaker functions. But just to compute mu, I must return back if only I have time. It's possible. And so we have this formula where psi lambda is just the rank n-1 function. And this is the basis of recursion. We write a similar formula for this rank n-1 case. We continue our descent up to the end. And at the end, we just get the free exponential. And so finally, we get this fancy formula, which is due to Lebedev and Kharchev, and which is called the Mellin-Bars representation. Mellin-Bars formula, the classical Mellin-Bars formula, it's valid in rank 1. In rank 1, we just get an ordinary differential equation for open Toda with two particles, so we exclude the total momentum. Then it's just an ordinary differential equation, and then the classical Mellin-Bars formula has precisely this form. But here, this is a far-reaching generalization of this formula. And so this my claim is that we must take this formula very, very seriously, because it's something, it's probably an indication of what happens in a much more general context in representation theory of semi-simple groups. The existence of this separation representations is something which the great classics of the subject have never dreamt of. So it's a capital thing to which I want to draw your attention. Now, there is a much more, well, this is a famous result which amplifies this result. Not only the quantum Hamiltonians of Toda can be realized by means of different separators acting on in the space of functions of lambda, but in fact the entire Lie algebra admits a representation in this space of these functions. So we just take these generators associated with simple roots of our algebra, and T is just the operator acting on one variable, and it is shifting its variable by minus I, which I is just the root of unity, root of -1, the standard imaginary unit. And the theorem says that this is a representation of our Lie algebra. Now it's something which hasn't got analogs in the former theory, because now it's the Lie algebra which is realized not by differential operators as usual, but by difference operators. And of course, much of the functional analysis has been developed in order to deal with differential operators acting on in natural spaces on Lie groups or on homogeneous spaces, and then one discusses the integrability of these representations, the representation under some conditions, representation of Lie algebra or of its universal invariant algebra can be integrated to give representations of the associated Lie group. Now, here the challenge is much more difficult, because we are dealing with exponentiation of difference operators, and I do not know much, unfortunately, about some general theory which deals with the matter. But this is what is needed. In fact, late Professor Gelfand, he knew apparently everything about representation theory, but he didn't know that. And I just imagine that if he were alive, he would have just he would have ordered to all his pupils and all his school should be just start working on the subject, because it's just a new chapter in representation theory where difference operators play the role of much more usual differential operators. So it's, a great work is required just to understand this context. And using this realization, one can find both the Whittaker vector and the spherical vector. And the spherical vector is again represented in this factorized form. So in this realization, not only the Whittaker functions are realized by this factorized formula, but also the spherical function. And this is the spherical function and this new realization. So this is again, it's a kind of totally new fact. Now, technically, the study of asymptotics of wave packets formed from spherical functions or from Whittaker functions requires much work, and it's a large part of the very complicated papers by Harish-Chandra. And here apparently things simplify because we are dealing with very explicit integrals with some gamma functions, and so we must compute the asymptotic state taking the Cauchy residue theorem, and then apparently the technical difficulties are very much absorbed by these factorized formulae. And now I must stop now. Probably I have exhausted my time, although I could not tell everything. In particular, I didn't tell anything about the computation of this potential measure. Roughly, the potential measure in Harish-Chandra's theory again appears from the study of asymptotics, and you get an integral, and this integral is computed by Gelfand, by Gindikin-Karpelevich, and although gamma functions appear in the answer, the difference equations for the gamma functions don't play any role. You just get some standard integral representation for gamma function, for beta function. And here, for the first time in this new derivation, which is due to Sklenin, when you compute this mu, you again get some difference equation from mu, from which you finally get the solution. The same one, of course, but now the difference equation satisfied by gamma or by beta functions, they are fully put into action. So it's again, it's aesthetically quite satisfactory. So this is basically my story, which because I must stop now. I think that there are two communities of people which are working on the subject, and one community is associated with the experts in representation theory, and there are higher chapters of representation theory which deal with global groups or with p-adic groups, and this factorization for the intertwining operator is valid in those cases as well. There is the Langlands program and much more. And on the other hand, there is this theory which comes from quantum and scattering method. And here people were interested in solving some explicitly solvable integrable systems, and all the implications which it may have for the representation theory, they still have to be worked out. So the aim of my talk is just to bring attention, maybe to establish some bridges between different people, just because they are discussing things which are interrelated, but in different ways. And so for me, it's absolutely certain that this is a new chapter of representation theory, and that the experts in representation theory should take it very seriously. But I must confess that I do not know much on these possible generalizations. So if we just look at the big papers of Harish-Chandra, which deal with the decomposition of L2 of G, with all various branches of continuous spectrum which arise in this case, which nothing is known about these examples. In the theory of integrable systems, the counterpart of this higher theory is probably the theory of Lorentz systems with internal spin. If we just take vector-valued Hamiltonians with values in some finite dimensional reducible representation of K, then we get some fancy Hamiltonians with extra dynamic variables, and this is what is probably needed to deal with these Eisenstein integrals from which I have started. But nothing has been done so far. So it's an open problem and a great challenge. So I'll probably stop now, and I thank you for your attention.
So thanks a lot for your inspiring talk. So questions or comments? So you can either unmute yourself or raise your electronic hand. So I have a number of questions, but maybe the audience has questions. Okay, let me start, and then you people join. Like one, maybe I have several naive questions. So this separation of variables that you described, is it just pure AN phenomenon, or for other types, it can also be done? The formulas, all those products of gamma functions
as far as I understand, it can be done for classical series. It has never been done in the full generality, that is, in the classification independent way, but for classical series, it's well known.
Or even for D? Okay, just a question, because like I think C, when you have A, more or less you automatically get C, but then D is usually more complicated. I don't know, just a question.
Well, I must confess that I have not looked myself in these cases, but as far as I understand, it's possible.
Okay. Maybe another question. So so those old results, right? Like whatever Gindikin-Karpelevich formula. So are they easily recoverable from the new technology, or how?
Well, of course, you just have this explicit formula, the Mellin-Barnes formula, and then you
but that's a huge integral, right?
Yes. This is an integral, but it's an explicit integral. It's a Fourier transform, the classical Fourier transform of some aggregate of gamma functions, and then you look for the asymptotics. So you just compute the nearest residues to the real axis, and this gives you the correct asymptotics. Maybe there are some subtleties just as to uniform convergence, something like this. But this should be not too difficult. In the case of Harish-Chandra, it is difficult. It's easy to write this asymptotic formulae, but just to prove uniform estimates, Harish-Chandra developed a rather complicated formalism of some integral equations, like in one-dimensional scattering theory. And from iteration in these integral equations, you can get the complete result. But it requires much work because you do not know the integrand. Just the integrand is defined in some implicit or just not quite transparent way. So you need much work. Here everything is elementary, and so probably it's not so difficult. Details must be worked out because I guess nobody has done it accurately up to the end.
Okay. I have more questions, but maybe like if the audience has further questions or comments, that's a good point. If not, yeah, let me continue. So how is it, this separation of variables, how is it related to, or is it related, you know, there is all this story of Dunkel operators and then of this double affine Hecke algebras, right? It's a little bit similar, right? You have some kind of Heisenberg type relations there, and there is also something like a Weil group in action. I don't quite remember the details, but is it similar, or is it the same, or is it related, completely unrelated?
Well, I'm afraid I cannot answer this question, but because I do not know that part of the story.
Because that's another major technology, right? This all relation to Dachau. Okay, I don't know. Yeah. That would be interesting to know how it is related. Maybe my final question. So you explained this story in representation theory, but one can, of course, probably imagine thinking of possibly easier stuff in Poisson geometry. How would this stuff play if you wanted to whatever introduce a Planck's constant and take a semi-classical limit? Right?
You see, as far as I see, quantum mechanics provides better means to discuss this occurrence, and because one important part of the story is just the existence of this sequence of transformation operators, which are unitary operators, and our eigenfunctions, they just provide us with, they can be just this system of eigenfunctions, nothing but the distribution kernel of these transformation operators, according to the usual logic of quantum mechanics. Now, in classical case, we must think about some canonical transformations, but this chain rule, which is so simple in quantum mechanics, is probably not so obvious in the classical context. So we, as usual, the quantum mechanical picture is much more simple than the classical one. So because here it's just the application of this Dirac's chain rule, which allows us just to very freely get from the original coordinate system down to this separated system, just by stages. And this is a fancy result. This can be probably done in quantum, in classical case as well. Must look at some kind of Darboux transformations or whatever. But I guess this has not been done explicitly so far. It's a good question.
Okay, thanks a lot. Any more questions or comments from the audience? If not, thanks again. Thank you.
Thank you. I was very glad to speak in this seminar, and I usually, when I'm free, I usually follow the seminar every time.
Okay, well, thanks a lot, people. If you kind of have more questions, please don't hesitate. If not, thank you everybody for taking part in Global Poisson this week, and we return in 2 weeks from now. Thank you again, and bye-bye.